All right.
Okay. Drew, you ready to take it away?
Yeah. Should we start?
Yeah.
Okay, great. Okay. All right. So this is the last lecture, and so we'll try to do as much as we can, and let's see how far we get. First, just two small comments. So you might recall we discussed entanglement of formation at some point, right? We defined entanglement of formation, which was defined in this way, that minimum of Pi SAI, if you write down density matrix as consider all possible decompositions of a density matrix in terms of pure state, and minimize this average. And we are still talking about only bipartite entanglement for each of these pure state. Phenomenon entropy is a good measure of entanglement. So minimize this average over all possible such decompositions. So just two very small comments. One comment, I think I had mentioned it's a faithful measure that it is zero if and only if density matrix is separable. That is very easy to see just because, so if it is separable, it's clearly zero. But if it is zero, then it's also obvious because each of these terms are zero, because sum of positive numbers. And how can positive numbers be zero? I mean, sum of non-negative number be zero if all of them are zero. So that shows that it's a faithful thing. That's one comment. Second comment is maybe more interesting, which was a question. One question that was asked was, how do we know that when we calculate something like negativity, which is not a faithful measure, so that is there exist non-separable states for which negativity is zero. So then we discussed that negativity in a Gibbs state has area law, and the question was asked that how do we know that the part which is missed by negativity is not very large? Maybe could it be volume law or something? I think that was one question that was asked, and that's actually so I can argue that's not the case. So the argument is the following: that there's a bound between entanglement of formation and entanglement of purification. So I will define that in a minute, but EOF is less than equal to entanglement of purification. So P here is purification. So what is this quantity? So the idea is that you are given some mixed state, some bipartite mixed state, A, B. Let's purify it with some additional Hilbert spaces A prime and B prime, and look at the entanglement between A prime and B prime. Because so this is a pure state, so Bornemann entanglement is a good measure. So minimize this over all possible such extensions where you have enlarged space. So that's called entanglement of purification. And you can show that that's bigger than entanglement of formation. Yes. Minimize over all such extensions. Because you're only given, your actual density matrix is rho AB. I can clearly construct infinitely many different purifications of it. I'm minimizing over all possible purifications to the whole thing is a pure state. So So it's not very hard to prove that this that entanglement or purification is bigger than entanglement or formation. And the argument is almost like one sentence that so consider the optimal purification minimizes this, which gives you this, and then trace over. And we know that look at the first look at the entanglement of formation for that optimal object. So the entanglement of formation for, let's say, optimal A prime with BB prime. Now for a this is a pure state entanglement. So this is equal to the your entanglement of purification. Now entanglement of formation is monotonic under partial trace. So then you can, so this is bigger than equal to, so trace out A prime and B prime. So that's it. It's a one sentence argument. So this side is the entanglement of purification, and this side is the entanglement of formation you are interested in. It is true, like it's one of those arguments. You may feel something is wrong, but it's true. It is correct. So this is then. Now the question is, what about entanglement of purification? This is actually not a good entanglement measure. Turns out it can be non-zero, even for separable states, but it has a property that find back. For example, this will be less than unoptimized purification by definition. So consider some purification which you can easily work with, because this is the optimized, be always less than the unoptimized ones. And they exist unoptimized purifications for at least very large class of standard condensed matter or local quantum field theories, for which we can find the unoptimized purification, which is still an area law. So one very famous one is field double state. If you have heard of this, basically you write down interested in some density matrix only over region, let's say A union B, you can define A prime B prime like this, maybe half here. If you trace out A prime B prime, you will get Gibbs state on AB, and thermofield double state, you can calculate its entanglement with this bipartition, and at least for a very large class of such systems, you can show using the standard field theory calculation. You can sometimes even find thermofield double state as a of local Hamiltonian gap, and so on. So anyway, I'm just saying there exists large class of systems where even this unoptimized one is area law, which is bigger than this and which is bigger than this. So okay, this is a comment. This was not like supposed to be the main thing today. So all right. So now let's get started with the last time we ended a lecture on defining the distinction between local and non-local part of negativity, and we wrote down this equation, which was En. We separate as En local plus En non-local, and we try to give some argument why the local part cannot have a constant term in 2 plus 1D because of some curvature expansion. Some almost like a Landau theory for entanglement. And so in 2 plus 1D, this part is something like L plus 1 over L plus 1 over L cubed, skips one term because of the argument we gave. So if you see a constant, something like minus gamma, that must come from non-local part. Okay, so now the question is, how do we use this to do something interesting? So the first application I want to talk about is distinguishing classical from quantum phase transitions. So now again, let's consider again maybe our canonical model for studying quantum phase transitions and also classical phase transitions as Ising model, let's say on a square lattice, transfer Ising model on a square lattice. So again, the phase diagram is like this. This is paramagnet, this is paramagnet, this is temperature, this is H. So now the question is the gamma here 0 or non-zero across this transition? So first of all, you may wonder, even could the local part be So what do we want? If we want to say some transition is, if we believe some transition is truly classical, in the sense that all its universal properties can be described using some factor field theory, which does not involve any quantum mechanics, then it makes sense to us. Can one find some quantity which we call, let's say, true quantum correlation, which does not even see the transition, right? That's maybe a high bar, but if you can find such a thing, then you're in good shape. And it's very hard to imagine such a thing can be found, right? You might think that if I look at any correlation function across a finite temperature phase transition, it will look singular, right? It's hard to imagine how can singularity not exist in any quantity. So that was that was one of the motivation for this question. So first we can focus on perhaps the local party and just a full EN across this transition. And I don't know how to do this analytically, but you can construct mean field like models where you can make progress analytically. Things like, yes.
The scale is local or
Non-local. There's no log L at finite temperature. No, I'm coming to it, right? I did not write logs so far anywhere. So yeah, there are no logs in this system. Even at 0 temperature, there are no logs. Even at this point, for a smooth boundary without any corners, it's L minus gamma. There are no logs. Anyway, so you can study mean field like models which still have singularity. It's just a mean field exponents. I don't mean like mean field without any fluctuation, like mean field with Gaussian fluctuations. So you still have interesting exponent for the correlation length. Nu is 1/2 or something, right? So then so you can study those models, and you find that En itself is singular across this transition. So that was the first, at least, puzzle. Yeah, you can consider like spherical like models, right? So yeah, so there are different versions of this. I know there are versions of this which can be made local by taking large Hilbert space local dimension and taking large n. So they're more like large in the ON spirit large n. Yeah, so there are different versions of spherical models when they're all-to-all coupled, where there's no notion of dimensionality, but you can also make Hilbert space dimension large. But effectively, what it means is you can just study like essentially you can ad hoc. I mean, you can just write down something like let's say pi x square is like a momentum, and phi of x minus phi of x prime square is like your conjugate variable, and and then you can make the mass term for phi to be a singular function of some parameter. So it's effectively captures that. It's not any when you solve the saddle point equation. So, but in any case, the point is it is a singularity in En, and the reason for that is the area log part of negativity is sensitive to short distance correlations, right? So if you look at the local part, but even short distance, I mean, expectation value of local operators is singular across transition. Energy density, for example, is singular across any transition. So that will get reflected in the local part. But that doesn't mean that there is some long distance quantum effect, right? It's this picture you have region A, region B, you have some perhaps short distance singlets. This is just kind of a cartoon picture, but the correlation, this kind of correlation between these local objects can be singular, and it is singular across such a transition. Energy density, for example, is singular. So so the thing is, you have to define some part of negativity which cancels out these things, and then you use your usual kind of argument that, as I already mentioned, as long as this decomposition exists, then you can do some ABC subtraction. You can define some 3 regions. Because there is an area law and this part is local, you can define some EN A plus, you know the 7 terms. I won't write down, but you know what I'm saying. A plus B plus C minus AB minus BC minus CA plus ABC, the usual thing we do to calculate ground state topological entanglement. I mean, the analog of ground state topological entanglement dropping in gap phases. Here we are not interested in whether something is quantized or not in this specific problem. We just want to know something is 0 or not, right? If this combination vanishes for all possible geometries at this transition, then you are convinced that there is no non-local term. So you can do that for these models, and you find it to be 0. So that's one interesting fact. And the second thing you can do is do quantum Monte Carlo, not on the negativity, but on Rayleigh negativities. And why? Okay, you might say Rayleigh negativity is such a, maybe this is, you pull out of hat some, basically, so you define some trace of rho transpose over B cube, for example, and trace rho cube, something like this. So you can, if you look at this object and then take log of this, so this is like a third Rayleigh negativity. You may ask, well, why not 2 here? If you do 2, it's actually 0. It's universal, but 0 is a universal number, but it's not very interesting. So then, so this is the lowest one you can study, and you can, and first of all, you can calculate this quantity for the models which you do understand analytically, like spherical models or these mean field-like models, and it has basically same behavior as the actual negativity. So that gives some confidence. It's not a bad quantity to look at. And then you go and study it using Monte Carlo. So this is this has been done, and what was found that although both of these species are singular, this is singular and this is singular across the transition, if you take the ratio, it completely cancels out. The singular part cancels out. And the reason this is singular is because von Neumann entropy is singular. So that's why this example is interesting, because this really provides an example where something like trace of rho log rho has non-local singularities, right? It as it should at any finite temperature transition, entropy is singular. But if you do partial transpose, and then that singularity somehow goes away. So that's an interesting fact, that is a sharp distinction between classical and quantum in these examples where you are at a finite temperature transition. So they are sometimes two length scales, quote unquote. One is length, the physical correlation length associated with correlation functions. So if you look at some OX O0, that decays e to the power minus some x over psi, where psi diverges, say 1 over t minus tc to the power some nu. But then there's length scale associated with negativity. So if you define this, let's say this typical length scale here is, let's say some L, you define this tripartite negativity, let me call it delta En3, that decays as e to the power minus some L over some psi quantum, let me call it. This is classical, this is quantum. This remains finite even at the transition, this quantity. So that's the main. So roughly speaking, the picture you should have is that they are roughly like some kind of if you like, some EPR pairs which exist up till some length scale psi q, which does not diverge at a critical point, and at finite temperature critical point, and then there's a incoherent sum of those things, which gives you classical fluctuation, which does diverge. So that's the picture of this, and you can even, at least for simple models where you can make some progress, you can even calculate psi q essentially analytically. Then psi q essentially goes as, at least for these relativistic models, this goes as beta. So which makes sense when you approach 0 temperature quantum critical point like here, then it diverges. Yes, I have several hands. Okay, let me start from left to right. Yes.
We do this subtraction, we stay only with the mean local term.
Uh-huh.
So classical phase transition is zero.
Yes. No. Add that. No. So this is the phase diagram. So first of all, let's look at various axes, right? So first of all, everything I've mentioned so far was along this critical line. I was not mentioning on whether. So the statement is everywhere here at any non-zero temperature, whether we are ferromagnet, paramagnet, why is this M? I don't know. Paramagnet at DC, high temperature, this part is just 0 in thermodynamic limit. Delta En3. Thermodynamic limit scale this also. I mean, because it's exponentially small in these regions. So that is always 0. Now, if you look at the, so that covers everything at non-zero temperature. Now at 0 temperature, then it's just usual entanglement story that you already know of, that this is a gap phase on both sides. So the entanglement is kind of, I mean, okay, there's GHZ-like entanglement here, but apart from that, there's not a lot of entanglement on the even on the paramagnet side. And the paramagnet clearly is really nothing there. And on the critical point, there will be subleading term like L minus gamma. Yeah, the usual, because there is some CFT. So for CFT, this is the usual form in 2+1D. So yeah. All right. I think maybe one, yeah. Yeah, that's what we are trying to do. Yeah, that's what we are trying to capture, the distinction between classical and quantum by using negativity as a tool. You could say that, yeah. I mean, that's a rephrasing in English, but yeah, but this is a precise statement. Yeah. Yes.
Yes, so I had one technical question. I one physical question. I forgot the definition. So why is there normalization by?
Because when you because you want to make sure if you define trace row transpose like the nth range entropy, you want to make sure when you take n going to one limit so that it should recover the negativity. So you have to divide by trace row to the power n. So that's
in the non-range. You write down the definition.
So that is one norm of partial transpose, right? So the way to take limit, you first calculate this for 2n, the really right thing to do is to calculate it for even integers, and then take limit even integer goes to 1. Because you are trying to take square root, right? Roughly speaking, you're writing mod of x as square root of x square, right? So that's why you have to do that. And in fact, people when they first missed this part and there was mistakes made and so on, but then they figure out very soon that this because of this. Anyway, yeah.
Plus the thermal transition, the quantum doesn't diverge, but you have some smooth thing.
There's a more side point there. So the psi q is finite at the but it may still have singularity. Yeah, it may have some cusp singularity because something is still there. I mean, it's finite.
Quantum transition, zero temperature divergent.
Of course, yeah. As beta.
The way you define classical is divergent.
Yeah, both diverge. Okay. I mean, I wouldn't at a quantum transition, I wouldn't call it classical because you're looking in the ground state.
Well, I'm just saying.
I want to call it psi classical only when I'm looking at non-zero temperature, right? Otherwise, when you're at a pure state, ground state, we should not call it classical. Everything is quantum in zero temperature.
By your definition.
But let's say at T not equal to 0. That's how I defined it, right?
All I'm saying is if you.
It does diverge, yes. Both diverge. Yes. Yeah, it diverges. Everything is power law at this point, right?
Then you look at the negativity. Is it diverging with the same exponent?
Yeah, because as we know, for the pure state, negativity is S1/2, so we know everything about it. Yeah, it has the same. I mean, your length scale will extract from it up till some obviously prefactor, like the exponents will get the same one. You don't care about obviously whether you call it 2L or L or 3L or something.
I thought you were advocating that. I don't. Does that? Is there a model?
Yeah, that's the next part, right? Yeah, I'm coming to that.
Well, I didn't say what they want.
No, you're asking, are there models where there's a finite temperature, is something interesting happens? Is that what you're asking?
The first one doesn't diverge.
Okay, that I don't. That we don't have, but we have examples where both diverge at finite temperature. Okay, yeah.
But the psi q, and under a normalization, psi q gets smaller.
Maybe it becomes, yeah. I would say, I mean, they still are. I mean, there is a length scale, thermal length scale beta, and if you like, yeah, I don't have answer. I mean, the naive guess is close to infinite temperature, you might think, like, so then it becomes 0. But I don't have any such, I mean, argument that it does. Yeah, but that's maybe an expectation, but I don't know. And much more than that, this is all some. I mean, look at the scale of things that have been done, right? Very little so far. I mentioned spherical models and some Rayleigh negativity. So there's much more to be done here, even just using standard field theory calculations. So there's more to explore. I'm hopeful more things can be done just in closed form using just, so even RG calculations haven't been really done. Yeah, but I'm saying because there's still, but because there is a fixed point here from classical point of view, right? So it doesn't, as I mentioned, psi q itself psi q remains finite, but it may have some cusp singularity while remaining finite. So that's why this may still have some notion of even if psi q is finite, doesn't mean you don't see it, right? It's still there. What you are, what you're trying to say is from quantum point of view, RG looks like this. You're making that's a very bold claim, right? But I'm saying there's still possibility that maybe it knows the fact that there's some singularity in psi q, cusp singularity may, even if psi q is finite, maybe there's still some sense it knows about it. I don't know. So no one has done these calculations, so I don't know. But obviously this will be much nicer, but I don't know the answer. Yeah. Yeah, it cannot. I understand psi q is if psi q is finite, to have a fixed point, you have to have something diverge. I understand that, but it'll be nice to be able to do that. Yeah, I agree. Yeah. So all right. So then the next topic I wanted to chat about was about so this is all kind of not that interesting, right? Sense that the conclusion is what you expected, so not maybe that new or exciting, but so the next topic is thinking about topological phases of matter and understanding how they behave in the presence of thermal fluctuations. So what should I do? Let me erase that. I think yes. Oh, great point. Thank you. Yeah. Yeah, I think that's why I wrote the whole thing, because my memory is so bad, and that's the whole point of writing that. So I wanted to, how much time? Let's see. Let me mention that. It's very interesting. So this is some sorry? I have one now. Yeah, but I think there are several things. So let's just so this is some. So I wanted to mention that if you're sitting at this DC, then density matrix has still obviously power law correlation, right? Trace of rho O is long range. Trace of OX O0 is power law. Some exponent. But we want to say that there exists perhaps a decomposition of rho as short range entangled state, right? Like some PI. So how can that be consistent, right? We might wonder. So that's why I want to introduce a notion of what recently a lot of people have worked on, is this notion of exact versus average symmetry. So this density matrix has what we'll call but now it is called average symmetry, that is U dagger rho U is rho, where U is the Ising generator of the Ising symmetry. U is just product over all sides X. But you can also introduce what we call, so when we have these average symmetries, there is no really contradiction of writing rho as sum of short range correlated states. And we can discuss that in a minute, why. But first, let me consider more interesting case where what we call exact symmetry. So let me, for example, so there the statement is if let's say U acting on rho, just one-sided, is some e to the power I theta rho, U some unitary operator. So this is what is called exact symmetry. So the work I want to mention very briefly is this recent work by Sung Cheng and Jay Hao is in the audience, and Sagar and Tim Shea, and where they use this notion of exact symmetry to argue under some conditions, density matrix cannot be written as sum of short-range correlated states, unlike finite temperature transitions. I want to make because at finite temperature transitions, you don't have exact symmetry. You only have so-called average symmetry. So the exact symmetries tend to be much more powerful to constrain, to rule out such separability. So let's consider one very specific case. So let's consider, let's say you have consider, let's say, Ising some Ising symmetry where, let's say, U acting on rho is rho. So you're given some mixed state rho which satisfy U rho is rho, and you're also given that trace of rho OX or 0 decays slower than exponential, where O is charged under U. So consider, say, Ising symmetry. So U dagger O, U is, let's say, minus O. So O is like, for example, Z operator. So the statement, which is proved in this very nice work, is that combination of this statement and this statement, these three conditions, rule out that rho can be written as sum of short-range correlated, short-range entangled state. So one would like to contrast this with this, because here we believe it is possible to do it because of the finite correlation length at finite temperature. So let's see how does the argument go. I will keep it brief because it's a very short and cute argument. So the idea is, let's first assume that rho is pi this. Okay, there's some, okay, no, that's on the assumption. Does consider any such decomposition. So because of this condition, each of these eigenstates, each of these pure states will be an eigenstate of U with eigenvalue 1, because that's why it's the exact symmetry. Because you can think of taking a trace on both sides. So this is the maximum value you could have taken. U has eigenvalue plus and minus 1, right? U is some, let's say, product of all the x's. So it means that U acting on psi I is psi I. Each of these is an eigenstate of U. Okay, so let's prove it using contradiction. So let's assume each of psi I is short range correlated. So if I get stuck, I have a co-author of this paper in the audience, so it's good. But I think we can do this. So the
Because it's Ising, cannot be bigger than 1 and less than 1. That's on average, they're 1.
no, that's the whole point. Because if you have sum of numbers, each think of this like, if even one of these was less than 1, then you will never get average equal to maximum, right? The average here is maximum. So that's why each of them have to attain that bound. Right? That's all.
The maximum is 1.
Maximum is 1, and you achieve that, and the average is equal to the maximum. So each of them have to be maximum. So then so the condition of psi I being short range correlated is that, for example, all the correlation functions should decay exponentially, connected correlation functions with respect to psi I. Because for example, mutual information bounds all the connected correlation functions and so on. So these things should decay very fast, exponentially. But every value of O is 0 because of the condition that O is charged under U. So because psi I is the eigenstate of U, you can put U dagger U here. So this is just 0. So this implies that OX O0 decays exponentially. Not just this part decays, decays exponentially, but that's a contradiction because we assume that, okay, yeah, so we assume this decays slower than exponential. And so now let's take trace of rho OX O0 is nothing but psi I OX O0 psi I pi I. Now we have shown that this decays exponentially and multiplying some positive numbers. So then this must also decay exponentially, but that's a contradiction with our assumption here. So this shows that our assumption must be wrong. It must not be possible to write down rho as sum of as a convex sum of short range entangled states given these three conditions. And the reason I'm mentioning it here, right here, because of this, what we just discussed there. There it was possible because we did not have the exact symmetry. We had only average symmetry in this sense, in a thermal state. So this argument does not go through. Because we assume, so what are we trying to prove? That rho cannot be written as sum of short range entangled state. So so we are proving by contradiction. So we assume that each side is psi I is SRE, and SRE implies that all connected correlation functions decay exponentially. Yeah, so I'm just saying that the thermal.
And the symmetry is not low.
Yeah.
That's why all this value always.
No, that's just because of,
Large is not low.
yeah, I'm just using the fact that the U dagger, you can say that. But
We know about spontaneous symmetry.
yeah, exactly. That's why I'm trying to just use this. Yeah. Anyway, you see what I'm doing, right? This become minus O, and that's why it's 0. So but I'm trying to say that the thermal bath tends to have this property that you have. In our Gibbs state, we just have what we now call average symmetries in this sense. U dagger rho U is rho, but there are possibilities where you can get these exact symmetries because of some specially designed quantum channels. So this is in this work they constructed. For example, you can imagine some case where you have decoherence. You have maybe two sublattices, A and B sublattice, and you have decoherence only on, let's say, A sublattice, not on B sublattice, something like that. So these kind of situations can generate sometimes analogs of these exact symmetries. That's one way to generate them.
The Gibbs ensemble would never have to check.
No, we don't, right? We can just check it. E to the power minus beta h acting on, say, product over all x in a transversal model is not equal to e to the power minus beta h, right? Yeah. So that's a setup. Ask Jay how the experiment will be done, right? Yeah, but it's I don't know. It's a way to think. At least it broadens your way of thinking about non-equilibrium states and so on. And yeah, you can have a phase factor. Yeah, I was just taking the simple example of Ising case. Yeah, sorry. I'm saying in general, as long as euro is e to the power I theta, U's are unitary, so it has some complex, eigenvalues. That's fine, but that argument still goes through. So yes. No, because they're multiplying by order of a number, right? But this is not bond dimension, right? Yeah, it's yeah. That's no, you cannot, because to think about so this is certainly less than the maximum value. Well, pick the maximum value here, the one with psi I, which has a maximum. The slowest decaying exponential. It's really less than that, right? Because pi is sum over all pi is 1. So you cannot ever achieve that. That's all.
So suppose I, in a real experiment, I couple my start at zero temperature as well, and I have a metric state under zero.
Right.
Now I couple it to a bath that is neutral under this,
Right. Right.
and I heat it up.
Right.
It can't really break the symmetry at that.
Right.
So
Right.
would that create such a?
I think that's maybe one way to think about that. That the bath has no charge. Yeah, something like that. Yeah. I think that's the perspective. Okay, I'm not. This is all kind of a bit new to me. I'm not. I mean, super expert, but I think the perspective in the work by Chong and collaborators is probably that the bath has no charge, something like that. But okay, yeah. But anyway, that was I think a side point. So let's move on to the next topic. So I defined it as mutual information, for example, decays exponentially. Yeah. Okay. So the next topic is thinking about cases where even a Gibbs state can be interesting. Okay, so then let's consider Toric code in various dimensions. So let's first draw. So let's look at phase diagram of Toric code in various dimensions. I will stop at d equal to 4. If you want to go higher, you're free to do it yourself. But d is spatial dimension. So first, let's look at just what we know, just based on thermodynamics. So we look at e to the power minus beta h. So h has this schematic form. There's something like an analog of star term, but in 4D you have to think a bit more. You can look at the notes, but there's two terms. It is a CSS code, so that there is one x term, and then there's some z term. Right. So I won't specify exactly the geometrical placing of different things, but that's a schematic structure which is shared by all three things. So when we are in 2 dimensions, there is no the only, in some sense, phase transition exists at only 0 temperature when you heat up. So there is no phase transition at any non-zero temperature, because we will discuss in a minute why. Okay, there's one simple way to see that. In 3 dimensions, there is a finite temperature transition where Tc is order Bp, and in 3D, in d equal to 4, there are 2 finite temperature transitions. One is Tc1, which is order, minimum of, let's take As to be less than Bp. That just depends on their relative strength. I just picked one choice. So that's what we know from just doing thermodynamics. So how would we have guessed this without doing any numerics? Yes. Yeah. I'm talking about as a function of temperature. Yeah, I just mean that if you go to, it's like saying 1D Ising model has a phase transition at 0 temperature, in the sense that the correlation length diverges. I'm just saying that in some sense the quantum length scale diverges even in the paramagnet phase, right? Let's not use that word, right? I'm not calling it a phase transition in a true sense. All I'm saying is that there's quantum coherence only at 0 temperature. That's all, right? So, okay, let me give an example. Suppose you look at paramagnet phase of the Ising model, transfer Ising model. Even there, you can define a coherence time, which actually is infinite.
Saying that there's a transition at here, turn on temperature from here to the patient. That's why. So,
No, I think, okay, let me define a phase transition as something where some quantity is singular. So let me give one quantity which is singular. So at zero temperature, topological entanglement entropy is log of 2. At non-zero temperature, topological entanglement entropy is 0. So that's what I mean by phase transition. That's all. That's all. So if you like that's all. I'm not saying anything more than that. So you can define again a quantum correlation length the way I defined there. That length scale diverges as you approach zero temperature. You can I mean, that's your nomenclature. I mean, I told you what happens, right? Then you can decide what you want to call it. I'm just saying you can calculate negative. I'm coming to all that, right? So you can calculate negativity in this 2D Toric code at finite temperature. It will be 0 at any non-zero temperature. At zero temperature, it is non-zero. It is log of 2. So how do you go from a non-zero number to a 0 number? There is some length scale associated with that. So there's some crossover length. If you're looking at distances much lesser than length scale, then you get 0 versus non-zero and so on, right? A usual notion. So yeah, I'm coming. I was first trying to explain. Yeah. So why is there no finite temperature transition here? Because here's one simple way to think about phase transitions in StatMac, right? If you don't have any local constraint, if you write H as sum of local terms, and if these local terms do not have extensively many constraints, then you don't have phase transitions. So for example, let me consider 1D Ising model, right? 1D Ising model is okay, let's see. I think we'll make it. Yeah. So consider 1D Ising model, right? It has, if you like, on a ring, you can call of these as tau I. There's only one global constraint. Product over tau I is 1. Consider 2D Ising model. You have terms on the bonds. So product of 4 bonds is 1, like S1. So there are extensively many constraints. So that's why 2D Ising model has a finite temperature phase transition. Now, if you look at 2D Toric code, there are no constraints because there's a star term, there's a plaquette term. There are no extensively many constraints in 2D Toric code. That's why 2D Toric code does not have a finite temperature phase transition. Now, if you look at 3D Toric code, there are constraints. If you take a plaquette term, okay, I'm going to erase this part. So consider 3D Toric code. There are 6 plaquette terms for each cube. Product of them is 1. So that gives you a local constraint. And that's why the TC of the 3D Toric code, that's why it's proportional to the plaquette term, not the star term, as already written there. Now, when it comes to 4D Toric code, both the plaquette term and star term, in fact, are on the same footing, and both of them have constraints. So they are two different transitions. In fact, the partition function of a Toric code is so Z is given by ZS, ZP, where ZS is both terms commute. So this is a classicalizing. This is a classical StatMac model. This is another classical StatMac model, right? So the partition function of Toric code is a product of partition function of 2 classical models, always, or in general for any CSS code. So that's why in D equal to 4, there are two different singularities associated with those 2 factors. Okay, so that's what we know just from thermodynamics. Any questions about at least this part? Yes. Yeah, because otherwise it essentially you can think of it like a Ising model, 1D Ising model, or zero dimensional Ising model. You can just call of each of them as SI and sum over them independently, right? So, okay, so far so good. So now we want to understand its quantum phase diagram, quote unquote, right? We want to understand, is there some quantum coherence at non-zero temperature? Okay, even before that, first let's look at the von Neumann entropy. Just trace of, let's say, so you have some Gibbs state, e to the power minus beta h, and you can look at, like, say, trace over some a bar. You can call it rho a, and look at trace of rho a log rho a, which is a classical. It has a lot of classical contribution, but it turns out that still knows about, I would say, it still has some universal subleading terms. I think the first people who calculate this were, I think, Claudio Chamon and Castelnuovo in 2000s, and they observed that there are these universal. So if you plot the universal part of this quantity, so look at trace to rho a log rho a, and look at some subleading term which is quantized, you'll find it is, in this case, it's just 0 at all temperatures. I mean, I'm drawing like this because there is some crossover length scale in is like 1 over log L. So if you take thermodynamic limit, it is really 0 at any non-zero temperature. In this case, it looks like this. So what I'm drawing, sorry. So the so here it is like something like log 2. This is like half log 2, and this is 0. I'm plotting the subleading term here. So I'm writing this S of A as some volume law term, some V, some minus some gamma. So we are plotting that gamma. So this is a classical correlation because we are looking at trace rho A log rho A. So the idea is, because here you still have some of the because you sort of, that's why I was using the word transition, you kind of lose as soon as you heat up, this part imposes really no constraint because there is no phase transition in this part in 3D Toric code. As I just mentioned, transition comes from this part. So that imposes some local constraints, and which leads to this half log 2. And similarly here, I think it starts from maybe 2 log 2 or something, but they are, as you can imagine, there is the steps of this kind. So anyway, but I'm just saying this is classical part of the entropy. And even in 2D Toric code, if you want to recover some classical part, you can consider a limit where, let's say, AS goes to infinity. Consider, let's say, AS goes to, let's set it equal to infinity in the very beginning of the calculation, right? So I'm taking thermodynamic limit, obviously, but first I send AS to infinity, then you will find that there is something like this. I mean, it starts at log 2, then it drops to half log 2, but it stays there till infinite temperature because you have some constraint. So so if you want to understand these phases where there is some classical entropy, you really have to think about this. So the rough picture is that the density matrix is separable, but it is a convex sum of states which have closed loops. So let me kind of give a physical kind of intuition why you have such objects. So it's still as just because you see such terms, you should not think it has some quantum topologicalness. So suppose rho looks like some over some, like essentially like product states, but the caricature picture is this. You have this sum over, I mean, yeah, sum over density matrices. This is a convex sum where each density matrix looks like some essentially a product state, but each product state has loops. So that's why it has some information about topology. So that's why you can store some classical bits in the system. So you can do classical topological computing. I don't think you'll get funding for it, but you can do that. So I mentioned this because these things also show up when we study decoherence-induced transition, as Ehud hopefully will discuss more, where, for example, if you take Toric code and subject it to only, let's say, bit flip errors. So initially, it will remain stable quantum memory up till some point, but at some critical value of the decoherence, you will go to a phase which still has some classical long-range order in broadly similar sense. If I'm not correct, I will correct me, but it's roughly the idea is that you have some classical memory left over. That's in 2D, because there you're not doing thermal. You're just doing something much more weaker than thermal, like some local bit of decoherence, like a short depth channel, not like some. Exactly. Yeah. No, you're not going to finite temperature there. There's no finite temperature. It's just a local. Yeah. Anyway, yeah, something like that. Yeah, but there's a threshold. But below that threshold, you are really stable quantum memory, because they are just doing something very mild, right, compared to heating up. So anyway, but I'm saying that it's good to kind of distinguish classical topological memory from quantum memories, and that concept shows up in all the time, like here, like this phase, if you take AS to infinity, or all of these phases. So now we contrast this with quantum memory, right? We want to characterize it. So again, we go back to looking at this subleading term in negativity, like delta E analog of this object for the Toric code. So what you find is the following. So now let me use the same plot. So En will be this color, the negativity, and let me look at the topological part of that. So in this case, despite the fact that there is, so this is a limit where I took AS to infinity, right? This is what I did, right? This is AS to infinity. So there is classical memory at any non-zero temperature. But that's a good thing about negativity. It does not care about it. So it becomes zero at any non-zero temperature. And why is that? What's the physical reasoning? Because once you send AS to infinity, you are suppressing your electric anyons, right? Electric charges. You are not allowing any placket that divergence of E becomes -1 or whatever, product over XX, right? Product over, if you send AS to infinity, then this is just 1. It's a constraint. So you don't have any anyons at any non-zero temperature, even at non-zero temperature. There's no finite density of electric-like charges. But you still have, because you're not sending BP to infinity, you still have finite density of magnetic charges. So that's complete. As long as you have some excitation, in Toric code has very simple structure, right? As long as you quote unquote condense one kind of anyon, you're just gone. There's nothing left. So heating up its bits like that, you're not condensed, but it is morally similar that you have just incoherent fluctuations of anyons. So you can't define braiding, right? If the thing can just move around freely, there's no notion of quantum coherence left. Of course, you can take both AS and BP to infinity, then you're back to the ground state. Then there is, of course, topological memory. So that's the, yes. Yeah, because I was looking at a measure of entanglement, which is not a good measure of quantum entanglement, right? I was looking at a measure of information, which is not a good measure for quantum information, trace of rho log rho, because rho is a mixed state.
You're just saying because it's not a good measure.
Oh, yeah. Yeah.
Okay.
But I'm saying we also have an intuition based on why it is classical based on the loop picture I gave there. There's a sum of convex sum of short range entangled states, but each short range entangled state has only closed loops. So you still have some global constraint, which knows about, that's why you get these extra gammas there.
Another question I had with this with the equals 4 picture, this term that you're plotting, it has like as soon as you get away from t equals 0, it still remains at the maximum value at the beginning.
Exactly, exactly. And we will come to that in a minute. Yeah, yeah. So right now we started from 2D. Let's go sequentially. Let me get some water. This is mine, right? This is okay. Yeah. Okay, so that's a picture in D equal to 2. You just get 0 at any non-zero temperature, and you can ask what is again the kind of a crossover length scale, if you like. It's like 1 over log L again, even for this negativity. So why is this 1 over log L? It's roughly related to the fact that as soon as you start having even order 1 amount of anyons, you destroy quantum coherence. So roughly speaking, so the density of anyons is like e to the power, let's say, minus beta BP, something like this. And that's like, let's say, 1 over, let's say, some polynomial L, or depends on what you want to look at. If you look at entanglement, sometimes this is 1 over L essentially, because you're looking at the boundary, you're trying to ask whether anyons are on the boundary, but you can even put L squared, doesn't matter for this scaling argument. So then you can get then T crossover is like 1 over log L, just by solving this equation. So that's the reason you have these crossovers in the negativity at 1 over log L then scale. Now let's look at the 3D Toric code. So again, maybe you kind of guess the answer. Despite there being a finite temperature phase transition, so this is your deconfined phase of the Z2 gauge theory here, right? So but it's not a quantum memory. This is how again negativity looks like here in this case. Yeah, deconfined phase mean that you can separate out to like if you create 2 charges, you can separate them to infinite distance without paying an infinite energy. So that's why it's a deconfined phase of this gauge theory. So the at high temperature phase is a confined phase, low temperature phase is a deconfined phase. And you probably know this from also, you probably have seen there's a duality between this phase transition, 3 plus 0 dimensional phase transition, and 2 plus 1D transfer Ising model, right? We can do duality also like that. I mean, anyway, but they are, yeah, there's a phase transition where one phase is confined, other is deconfined. And what happens to the? I mean, transition is visible in every operator pretty much. So, I mean, it's a thermodynamical transition. So
on average, product of Z's over large loops.
Yeah, something like that. Exactly. Yeah. You have one side you have large loops, other side you don't. So or membranes, if you like. Yeah, in this case. So and now let's come to the most interesting example here. You have a stable memory up till this point. As long as you have not, as long as one of them survives, in the sense that in load, so what's the physical picture? What's going on? So okay, I should have mentioned that. So right, so I already kind of hinted here. Here you have point-like charges, right? Here the ground state here is sum of closed loops, So the excitations are open strings. So, I mean, excitations are ends of open strings, if you like. So these are your electrical or magnetic charges in the 2D Toric code. So there's a finite. So at any non-zero temperature, you have finite density of excitations. In this case, again, in the 3D Toric code, you still have point-like electric charges. Your magnetic excitations are open membranes. So the magnetic excitations are open membranes, but your electrical charges are point-like particles. So at any non-zero temperature, you have finite density of at least one kind of anion. Other one is suppressed up till Tc. But as I mentioned, as long as you have one kind of thing, one kind of anions in this setup, then you're done with. You don't have any quantum coherence left. But here, both AS and BP associated excitations are loops, which are open membranes. So, and they have braiding with each other and so on. So, so this is a finite loop tension. So again, if you make energy entropy kind of argument, if you ask delta free energy is delta E minus T delta S, energy associated with a string proportional to the length of the string. There's a string tension. So this case as L, how many strings you can draw of length L, like e to the power L. So the log of that is delta S. So something like this. So there is a, if you like, some Tc, which is non-zero because of both of these terms scale with L. So below some Tc, you suppress large loops because of this free energy argument, and that's this regime. Both kind of loops are suppressed. So then have a stable quantum memory, and of course this argument is known for a very long time. Like so this expectation is I mean we knew from thermodynamics that there is a finite temperature quantum memory. It's not a new fact based on some negativity or anything, but negativity kind of confirms that okay, at least it captures. It's also a test of negativity as a good measure, let's say, right? So so I highly recommend this paper, this quantum topological memory from 2002. It's also an introduction to error correction. Sorry? Some unknown people. I'm just kidding. I mean, I think it's Kitai, Preskel, Dennis, and Landau. Anyway, so anyway, so anyway, but I'm just saying, it's a fun paper in many ways. It has a lot of stuff. And sorry?
The energy argument doesn't work for those ones. So you have to.
It works, right? In the sense that you still have a phase transition up till that point. So it works out. In fact, you can argue from free energy argument, even this part, that there are two steps, because below Tc1, not proliferating neither of the two loops. So that's why you have a stable classical memory up till that point. At Tc1, you start proliferating one of them. So that one goes away. And above Tc2, both of them go away. So everything is consistent. Yeah. Yes.
It feels a little bit too slick. The loops, it's not like there's two independent types of loops, flavors of loops with different light tension. Then you could say this, but like
They are.
the loops are.
It's a partition function is a product of two partition functions. Each of them correspond to one kind of loop excitation. There are two.
Loops are made up of operators that don't not trivial values.
Yeah, but
Why you could incorporate one type of loops impacts for the other loops.
it does. That's why the topological memory goes to 0. That's the whole point. As soon as we proliferate one kind of loop, the quantum coherence is gone, but the thermodynamics still survives of the other one, right? So you are completely correct. It affects it, but that's why it went to 0. And if you want to mimic this physics, you can ask, okay, this is 4D, this is great, this works, but we don't live in 4D, so what do we do? Okay, right? So, so you can mimic that physics in this case, in 3D Toric code, if you send AS to infinity from the outset, right? Then you have suppressed your bad guys, their point-like charges. And then you can convince based on, again, at least, okay, so the negativity calculation is hard to do in closed form. It's like a low temperature expansion which converges. So you can argue up till what temperature it converges, and you can make heuristic argument it converges up till the TC of your StatMech model. So using similar kind of argument, you will in this case you expect it to survive up till here if you take BSS2023. Anyway, yeah, but I suspect more can be done in these. I mean, clearly, even numerically, no one has, I think, done. I mean, it'll be nice to someone to do this calculation using quantum Monte Carlo. It's like a bit painful, like trace rho transpose cube or something, but I think it should be done. But anyway, so that's yes. No, please.
You mentioned the sudden death.
Yes. Right. So we don't. I think that's first. I think in this case, I don't know the answer. Because no one has calculated it, negativity analytically, right, in a closed form. We have some expressions based on kind of expansions and so on. So, in all of these numbers are probably scaled in the same way, like proportional to AS or BP. So it's possible that it can sometimes be below that. But I would think it's a non-universal feature. So if you tweak your parameters, suppose you add let's say transverse field or something, or make it more general with the same phase, you can push it to high enough temperature. So we actually had that in some of our spherical models when we were trying to detect various features of negativity across transitions. I think there were cases where the sudden dead temperature was hindering our knowledge of negativity because of that. Yeah, in some part, that's what I recall. It's been some time, but then we were able to push it around. So you might but the question again is, okay, is there some physics of the sudden death, right? I understand that, but at least my naive intuition based on how it works in CFTs where we can calculate things is real some short distance physics, which is it's not, as far as I know, it's not some super universal physics, but it's I may be wrong, right? It's nothing. These things are still not as deeply understood as one would like. So yeah. Yes. This is the only thing you can do in quantum Monte Carlo. Similar to when we study, for example, if we want to study ground state entanglement in numerically, no one knows how to calculate trace rho log rho, right? Log is a bad function for Monte Carlo. So we can calculate traces. So I'm just saying numerically it's easier. And even analytically, often you don't calculate trace rho log rho, right? You calculate there's no, like as someone famously said, entanglement is not well defined in quantum field theory. I won't say who said it, okay? But anyway, but it's some, because you only calculate replicated stuff, but it's all right. So where do we stand? Okay, so we at least covered some at least we have some intuition now for these things. There's still, I think, things to be understood, but at least it's some hint that negativity is not a super bad quantity, right? So kind of matches with our intuition. So at that point, I don't know how much Ehud will discuss this, but I should at least describe in words the recent work done by Ehud and collaborators trying to. So that's the basic idea is you start from let's say ground state of Toric code and do a short depth channel. So the simplest cases, for example, channel can be a bit flip channel or a phase flip, whatever. I mean, Z and X kind of terms. The cross operators are either local Z or local X, and you apply this channel on all sides, composition of channel on all sides, and you're doing short depth channel. So why are we doing this? This is so that when you have, so that we discussed just now that a Toric code at finite temperature is not a good quantum memory in 2D or 3D. So implication of that is that if you want to use it for quantum computing, you need to do active error correction. So if we lived in 4 dimensions, which unfortunately we don't, we won't need to worry about, most of the time we will not need to worry about error correction as much, right? I mean, suddenly if you work with 4D Toric code, you don't need error correction. It's just stable quantum memory. So, for example, like right now in your computer, right, you're not like looking and trying to correct errors because you have a stable classical computer. So, yeah. So, so if you want to use these topological models in 2D or 3D, we need to do active error correction as far as we can tell, unless someone comes up with some completely new model, which is stable quantum memory in 3D, we don't know. But so then the idea is, how are they interested transitions as a function of rate of decoherence? And decoherence is not same as coupling it to destroy everything, but some much more milder thing. Like as I mentioned in my first lecture, maybe someone like some cosmic ray coming and flipping your qubit, something like that. So one can understand. So there's some threshold to this. I mean, there's some stability. That's where all these threshold theorems, famous theorems from 1990s, come very handy. So there's some non-zero threshold as a function of your rate of your errors, and below that threshold, it's a stable quantum memory. And then you can understand that loss of quantum memory again using negativity, as recently done in these works by Ahud and collaborators. So that's when I think a interesting application. And but in those papers, which I strongly recommend you to read, they have more than one diagnostic. It's not just negativity like this. You can do a few other things. I mean, there's also this, in this double Hilbert space, you can work this error field double formulation. And there again, if you, for example, I don't know how much you're planning to cover, a little bit. But let me just say in one sentence, which somewhat relate to some of these things, which is that when you work with this double Hilbert space formulation, which I won't introduce, but okay, if you know it, you know it. If you don't know it, okay, you will learn it in your near future. So then, but there you do sometimes. I mean, for example, if you have only phase flip errors, you start from, in the double Hilbert space, you have 2 copies of Toric code. So without any decoherence, your topological entanglement entropy is 2 log 2 because 2 copies. Then when you go a transition to the non-topological quantum memory phase, then actually it does not go from 2 log 2 to 0. It goes from 2 log 2 to log 2. So I think that's, at least there's a parallel of that with that. Actual calculation of negativity of many body systems. So at least let's work out one example in next 10 minutes. I think that will be nice to see. And at least it will have some hint of the kind of calculations that go into Toric code. So let's just quickly do one calculation for a cluster state Hamiltonian in 1D. That will also show sudden dead temperature and so on. So that will be nice to see. And so you have a question? I think we discussed that, right? So but what do you mean? I mean, it is here. So you're asking cases where the topological, I mean, where the classical part stays robust up till some point, and but the quantum part does not in that regime. That's a good question. How would that occur? Yes, it's hard to imagine in simple. I mean, if something is happening with a quantum part, it means some kind of anion did something, right? So then one imagine that that constraint is gone. So something should happen on the classical side also, because I mean, the classical part is not truly classical. It has everything, right? It's sensitive to both classical and quantum. So that's why it's hard to cook up such things. But maybe there's some way, I don't know. Yeah. Okay, so now let's do a actual calculation. Actually, I had a couple calculations in mind, but I think the right strategy when you have to pick out of two topics, out of one is to, this online there's a random number generator which uses Bell pairs. So you can really generate true quantum random numbers. There's an online thing. So then our word line will kind of become like, I did one thing, entangled, you know what I'm saying. So then, I mean, if you believe in quantum mechanics, that must be happening. There must be some universe where you learn the other thing. So, sorry? I think that's the part which is hard, right? So it won't be random then. So, right. So, all right. I mean, I actually did go to that website. I remember the first number was 0. So let me imagine that I made some decision based on that for now. Okay. So anyway, so so let's look at Gibbs state of the following Hamilton. So let's you if you haven't seen this Hamiltonian, that's fine. But let me define it only 6 sites. It turns out doesn't matter how many sites you have because it's area law. And so let's to have less clutter. So let me work with, so it looks like, let's say Z1, X2, Z3, and so there are 6 sites and 6 terms, which all commute with each other. So this is called cluster state. Yeah. But I'm right. Sorry, Z4. Sorry. What would I do? So the 1, 2, 3, 4, 5, and the last one is just Z5, X6. Okay. Yeah. All right. So you can see all terms commute with each other. So 6 constraints, 6 qubits. So ground state degeneracy is 1. There's no, I mean, whatever. There's a unique ground state. Okay. So now we want to calculate, but what do we want to calculate? We want to calculate e to the power minus beta h partial transpose over B, where I define A as sites 1, 2, 3, B as sites 4, 5, 6. So we first want to take partial transpose, and then we want to take its one norm. So at least let me, I mean, yeah, in the interest of time, I will at least try to show you the main steps. It's not super hard after that. So the key observation is that the only non-trivial part of partial transpose comes from those terms which straddle across A and B. If something is only in A or some term, it does not give any contribution to negativity, because roughly speaking, the bulk part of the, you can call it like e to the power minus beta h bulk plus h boundary partial transpose. The bulk part, e to the power minus beta h bulk, is a valid density matrix, and it doesn't kind of enter in the partial transpose. The only thing that you have to worry about is the boundary term, and that will become clear now why that's the case. But let me just expand out these terms. All terms commute, exactly. That's why these commuting terms makes things. That's why the Toric code calculations are doable. Yeah. So very much like classical Ising model. So you can write, for example, this is like 1 plus tanh beta, and so on, right? So everything looks like 1 plus tanh beta up to some. I took out the cosh part outside, but that's just some overall factor. So let me call these terms, just for nomenclature, let me call this term S1, S2, S3, just to keep my life simple. But this, so this thing straddles across the boundary, right? Z3, X4, Z5, and this. So what are the two terms? So the first one does not, 1, 2, 3 does not, 2, 3, 4 does. So there are two terms which go across, the 2, 3, 4 term and the 3, 4, 5 term. So that's where the partial transpose enters really in a non-trivial way. So and when I write my note, hopefully this notes will be done at some point in the next 2 weeks. I will post them, and then I can put in more details, but this can be followed in real time, right? So it's not super hard. So let me call this S1, S2, and S3, S4, S5, S6. All of these are Ising variables. S1 to S6. So as I said, a bulk part is kind of trivial. So let's just take it out. It will completely go away. So let me not even write it. So let me write only the part which is non-trivial, the S3 and S4 part. So that is some e to the power. So this is 1 plus tanh beta. X Z Z2. Sorry. Yeah, I think I made some. Yeah. Z2x3. First one is Z2x3. Z4. Second is 1 plus tanh beta. Z3 X4 Z5, and I want to take partial transpose over B, and there's a normalization factor of 1/2 square because of just the way things have to be normalized. Like trace of the rho transpose is trace of rho, so there are two terms here. So then what is partial transpose? Remember, the y goes to minus y under partial transpose, x and z don't change, and or if you do partial transpose, meaning only transpose in region B. So when you the Z2 of course can't contribute to partial transpose because Z2 in region A. So there's a X3 times Z3, that is Y3, that also does not contribute to partial transpose because Y3 is in region A. But there's a Z4 times X4. Z4 times X4 is Y4, and Y4 goes to minus Y4, right? So before doing the partial transpose, if I multiply these two terms, this I call maybe S3 and this is S4, right? Before doing the partial transpose, this was 1 plus. So I should say this calculation I first learned from Tim Shea. So I thank him for teaching me some of this stuff. So 1 plus, let me call tanh as just t, just for saving my time. 1 plus t S3 plus S4. And so before doing partial transpose, it's something like this, right? They're just so far so good. Once you do partial transpose, the S3, S4 terms get a minus sign. So once you do partial transpose, this becomes so 1/4, 1 plus t S3 plus S4 minus t square S3, S4. Now this is no longer a valid density matrix necessarily because of this minus sign. So this is your rho partial transpose over B. And what is negativity? Negativity is the modulus, sum of the modulus of eigenvalues of this matrix, right? So there are 4 eigenvalues because it's two eigenvariables, and it's everything is classical, right? In the sense that S3, S4 are just numbers plus minus 1. So we know you don't have to diagonalize any matrix. It's just 4 numbers, take their magnitude, and be done with it. So all you have to worry about is whether that number is positive or negative. And that's what the condition, that's where you have to think a little bit, but that's all. So let's do that. So what are the 4 eigenvalues? One is 1 plus, so S3, S4 eigenvalues. So both are plus 1, both are minus 1. Right, this is it. Now I have to take mod of these and sum them. These are anyway positive. So the only condition is when is this positive or not, and that you can check that I don't remember one of them becomes negative at some temperature. So if they're both positive, then negativity is just 0, right? Because negativity only sensitive to the ones become negative. And actually, it's in my note. Let me just use because I did that calculation and sorry. Huh? I'm not doing any trace. It's a mod of. Sorry. Because I said the bulk part just drops out because of the normalization. Yeah. So it's easy to see just by plotting it. I think it's like old-fashioned way. Just if you look at this function between t is from 0 to 1, right? Tanh. So if you look at first function at t equal to 0, it is 1, and then it is plus 2t, so it goes up at short, but then it tries to go down, but it's not enough to take you down ever, because it's 1 and t equal to 1, it is 1 plus 1, it is 2. So this is always positive. This can become negative because it starts from 1. Both terms are trying to take it down, right? It's something like this. At some value, it becomes negative because it's t equal to 0, it's 1. At t equal to 1, it is 1 minus 3 is minus 2, right? So then, yeah, so you have to just find when is this number positive or negative. You have to find zeros of this thing. You do that, and the final result is that for t bigger than tc, which is when the negativity is non-zero, because tanh is large, you get 1 plus the sum of all these terms is 1 plus t whole square over 2. You can just check it, right? Because when this becomes negative, you have to just flip its sign, some everything, you will get this. So this is your negativity, log of this. And when t is less than tc, high temperature limit, negativity is just 0. So that's your sudden death temperature. Sudden death temperature is given by finding the root of this equation. It's like square root of 2 minus 1 or something. Yeah. So tanh is, yeah. So that's it. So that's the calculation. Okay, this is just one Hamiltonian. Why bother about this? But the main message is whenever you have some stabilized commuting projector Hamiltonians, especially CSS codes, what you will find is that the negativity calculation becomes partition function of some one lower dimensional system which lives at the boundary. Bulk part completely essentially goes away. Okay, there are some subtleties there when the bulk has constraint and it really doesn't decouple. Right? It's not super easy always, but at least in cases where bulk doesn't have any local constraints, you can decouple it. And then that's why 2D was easy. I mean, and okay, 3D is somewhat easier, 4D is harder, but nonetheless, it becomes some boundary theory at least in some cases. And there's also this very interesting work by Sagar and Sung Cheng, where they show that the 3D calculation, this boundary theory, becomes basically like a one-form 3D cluster model, which has a finite temperature phase transition. So that can be, so the quantum memory transition can be related to one lower dimensional finite temperature phase transition in a one-form cluster state in 3D. But most of this calculation do require kind of mapping things to one lower dimensional system using similar trick. Here we mapped it to a 0 plus 1D system. 2D Toric code you map to a 1D system and so on. Yeah, you have to just basically find y's. You're tracking where the y's appear on only one side, and you flip them and make it a StatMech model of that. I mean, there are many tricks. You can look at the papers, but the rough idea is always starting from something like this. Yeah.
So if you've added terms which were irrelevant, leaving you in leaving you in the 1ds your temperature, would that change with the sudden death?
I didn't get the question, I think. Right. I'm sure it will change. Sudden death is completely non-universal. Yeah. Right. So that's, I think we are already 10 minutes over time. So we will skip the last thing. Hopefully that's done in your counterparts in that other universe. But all right. That's all. More questions? You must be hungry, right? Okay, this is not lunchtime. Sorry, I'm hungry probably, but I haven't had breakfast. So.